Example 3.9 on page 99 in your textbook states the following. The drainage from a community during a storm is a normal random variable estimated to have a mean of 1.2 million gallons per day, MGD, and a standard deviation of 0.4 MGD. So we have a normal distribution with parameters 1.2 and 0.4. So we have a normal distribution of 1.2 and 0.4. If the storm drain system is designed with a maximum drainage capacity of 1.5 MGD, what is the underlying probability of flooding during a storm that is assumed in the design of the drainage system? So what we're looking for in essence, and this is really often the crux of the problem in this course, is understanding what is being asked of you. In this case, we want to know what's the probability of flooding during a storm, and you're given that the maximum capacity is 1.5. So we're looking for the probability that our random variable x is greater than 1.5 MGD. We'll drop the units here for clarity in this illustration. But we don't like to use greater than. We want to switch that around to everything that the inequality being less than or equal to. So what we say is the probability that x is greater than 1.5 is the same thing as 1 minus the probability that x is less than or equal to 1.5. So what we need to do, this is a standard, this is a normal variable, but we want to use the tables in the book, so we need to transform x into s. So the way that we do that is through our transform. So we have this being equal to 1 minus then the CDF function. And remember, when we transform, we take the variable x, we subtract off the mean, 1.2, and we divide by the standard deviation, which is given as 0.4. And this gives us 1 minus the CDF function of 0.75. So we go into the back of the textbook in table A.1 and we find that this is 0.7734, which gives us an ultimate value of 22.7%. So recall, so x being greater than 1.5. So if this is just a sketch of a standard distribution, if this is 1.5 out here, what we're asking for is the probability, let me undo that. What we're asking for is the probability that x is greater than 1.5, and 1.5 being here, we're looking for the probability that's here. But the way that the tables are structured in the back of the book, it's easier to ask the opposite question. What's the probability that it is less than or equal to 1.5? And we know that the whole area is equal, underneath this curve, is equal to 1. So we'll just subtract 1 minus the probability in here. The same thing. And that's exactly what we do. So this probability is, let's say, p, and this probability here is 1 minus p. So that's what we're doing in this first part. The second part asks, also of related interest, are the following. The probability that the drainage during a storm will be between 1.0 MGD and 1.6 MGD. So in notation, we're asking for the probability that x is going to be between 1 and 1.6. That's the probability that we're asking for. And we saw this in the lecture notes, where this is the CDF function of the transformed variable x into s, which means we take the value 1.6, subtract off the mean, which is 1.2, divide by the standard deviation, 0.4, minus the other limit, the CDF function of 1 0.0 minus 1.2 divided by 0.4, which is the CDF function of 1 minus the CDF function of minus 0.5. So when we look this one up in the tables, we get 0.8413, and we subtract off of that. Remember, when we have a minus, it's the same thing as 1 minus the positive value. So we got 1 minus the CDF function of the positive value. And when we look that one up and crank it all out, we end up with a value of 0.533. So we just go back to the back of the tables and we look that up, and we find that this value is 0.6915. When we plug that in, we end up with the final result of 53.3%, that the random variable x will take on a value less than or equal to 1.6 but greater than 1. So that would be in here, 1.6 and 1.0. What we want is the probability between these two in here. And the way that we do that is first we take the probability, and change colors on here to make it a little easier to see. Let's do this blue. For 1.6, we take the probability, all of this probability, in blue down to minus infinity, and we subtract off of that the probability that it's 1. So let's make this one red. Here and down. And what we're left with is the gray area, or the original area in between. And that's all we're doing when we get a problem like this. Final question asks us for the 90th percentile drainage load from the community during a storm. This is the value of the random variable at which the cumulative probability is less than 0.9, which we would obtain by the following. So we're asking for the 90th percentile, that the probability that x is less than or equal to some value x at the 90th percentile. This is the CDF function of our value x at the 90th percentile minus the mean divided by the standard deviation. Oh, that's 4. We want this to be equal to the probability, the 90th percentile probability, so 0.9. If we take the inverse of both sides, what we have is the inverse of the CDF function. The inverse of that is going to be simply everything that's in parentheses. So x at the 90th percentile minus 1.2 divided by 0.4 is equal to the inverse CDF function of 0.90. So from table A1, we go and we look for the CDF function of 0.9. And we find that that's associated with an x value of 1.28. So let me put here 1.28. So all we simply do is cross multiply, add, and we end up with x at the 90th percentile is equal to 1.71 in the units of MGDs. This is an x. So we asked just the opposite. So we have the probability this time, and we're asking for the value that's associated with that probability. So we're asking the inverse. So we use the inverse relation that we talked about.